Here are the solutions for this week's Check for Understanding that covered Chapter 4. Find the domain and range of f of x is equal to log of 2x minus 1 plus 3. So the log function is defined only for numbers which are greater than 0. So we know that for the domain, 2x minus 1 must be greater than 0. So if we solve that, we'll see that x has to be greater than 1/2. So the domain or x greater than 1/2, or if you wanted to write that in interval notation, the open interval from 1/2 to infinity. And the range is all real numbers. Here's an exponential equation to solve. To solve an exponential equation, we need to make sure that the base is isolated. So we need to get rid of the 3 and we have to get rid of the 4. People often remember to get rid of the 3 by adding it to both sides, but they sometimes forget that the next step is to then divide both sides by 4 so that the base is by itself. So e to the 3x is equal to 10/4, which you could reduce or make into a decimal. Now we can take the log of each side, and it's often easiest to use a natural log. By the power rule, we can bring down the power now. So 3x times the natural log of e is equal to the natural log of... since this is a friendly decimal, I'm just going to go ahead and change this into a decimal and write the natural log of 2.5. Now, the reason we like to use the natural log is because we know that the natural log of e is equal to 1, so we can ignore it. To solve for x, we simply have to divide by 3. And so x is equal to the natural log of 2.5 divided by 3, and that gives us a value about 0.305 if I round off to 3 decimal places. Next, we'll solve a log equation. To solve a log equation, what we want to do is we want to make sure that at most we have one log on one side of the equation. So we're going to start by subtracting 3. And if we subtract 3, then we'll have the natural log of x plus 2 is equal to 9. If there was a log on each side, we could cancel them. When there's only one log, the only way to get rid of it is to rewrite the problem using exponents. Since this is a natural log, we know that the base is e. So e to the 9th is equal to x plus 2. So to solve for x, we simply subtract 2. So e to the 9th minus 2 is equal to x. If we wanted to do an approximation for that, we would approximate that by saying that x is roughly equal to 8,101.08. And finally, we have 2 application problems. So this population model models the population of a city. P of t is equal to 325,124 e to the 0.12 t, where t is measured in years. So A, what is the initial population of the city? There's 2 ways to do that. You could just remember that the initial value is this number here in an exponential growth formula. Or another way of remembering that is if t is equal to 0, in other words, at the start, then this power would be equal to 0. Anything to the 0 power is equal to 1. And so either way, we know that our initial value was 325,124. When does the model predict the population will reach 340,000? That means we have to solve this equation. 340,000 is equal to 325,124 e to the 0.12 t. So again, this is an exponential equation. We need to get the base by itself. To get the base by itself, we're going to start by dividing. That'll give us the base by itself, and then we'll take the natural log of each side. So the natural log of this fraction here is equal to the natural log of e to the 0.12t. The reason we did that is so that we can bring this power down. So on the right side, we're going to have 0.12t times the natural log of e. We know that the natural log of e is equal to 1, and so to solve this for t, we would have to divide both sides by 0.12. So if we take this and we divide it by 0.12, we're going to have our value for t. So let's see what that would be. We have the natural log of this kind of gross fraction, which we'll then divide by 0.12. Let me try that again. I think I lost a 0 somewhere. Let me just make sure. So we have the natural log of 340,000 divided by 325,124. And we're taking that value and dividing it by 0.12. Oh, well, we have a t equal to about 0.37. So according to this model, the population is going to reach that level in a very short amount of time. Last problem. A doctor prescribes 400 milligrams of a drug that decays by about 0.15% each hour. What is the half-life of the drug? How much of the drug will remain in the patient's system after 24 hours? I think I'm going to have to break this video up into 2 parts because YouTube will only allow me to upload a 10-minute video. So I'll do this next problem in a part 2 video.